Hey everyone, and welcome to The Explainer. Today we're diving into the world of computer science. But trust me, this is a story for everyone. We're going to uncover a hidden law inside one of the simplest algorithms ever created. A story about finding predictable order right where you'd least expect it.
So think about it for a second. When you shuffle a deck of cards and then start sorting it, does the path of each card just seem totally random? Pure chaos? Or are there some kind of invisible rules guiding where everything ends up? Well, that is the exact question we're digging into today.
All right, let's get right into the heart of this mystery. Our story is all about a classic sorting algorithm. It's really famous for being simple, maybe even a little inefficient. But it turns out that very simplicity is what holds a really fascinating secret. So meet bubble sort. The way it works is, well, it's pretty straightforward. Imagine you have a jumbled list of numbers. Bubble sort just plods through it over and over again, comparing two numbers right next to each other. If they're in the wrong order, it swaps them. That's it. The bigger numbers kind of bubble up to the end of the list. Its simplicity makes it the perfect little laboratory for watching how numbers really move around. And here is the central mystery we're investigating today, something called the pairing effect. The question is, when a number gets moved during the sort, does it have a special tendency to land right next to its numerical sibling? Does a 5, for example, end up next to a 4 or a 6 way more often than you'd just expect from random chance?
So the first time someone really dug into this question, they found a very, very intriguing clue. It really seemed to suggest that, yeah, something pretty unusual was definitely going on under the hood.
Get this, an early, small-scale experiment turned up a pretty surprising result. It found that when a number was swapped, it would land next to its neighbor a whopping 60% of the time. Now, based on this, it looked like pairing was actually the rule, not the exception. But here's the thing about small tests, right? They can be super misleading. Was this 60-40 split a fundamental law of bubble sort, a deep truth about how it organizes data? Or was it just an accident, a ghost in the machine that would totally disappear if you just looked at more data? To find the real answer, researchers knew they had to go bigger. I mean, much, much bigger. So they designed a whole new experiment to settle the question once and for all. And they were incredibly thorough. They took these huge lists of numbers, 1,000, 5,000, even 10,000 items, shuffled them all up, and ran bubble sort again and again. But the crucial part is they logged every single swap. Every time a number moved, they tracked where it landed. We're talking about millions and millions of data points. Okay, so after all that number crunching, the verdict finally came in, and it completely, totally overturned that initial clue. The reality was something else entirely. Just take a look at this table. It doesn't matter if the list had 1,000 items or 10,000. The results are incredibly stable. See that no pairing column? It is consistently hovering right around 77 to 78%. The pattern wasn't a fluke. It just wasn't the pattern everyone thought it was. So this is the real picture. That initial 60-40 split, turns out it was a mirage. The truth, revealed at a massive scale, is that about 78% of the time, a swapped number does not land next to its neighbor at all. Pairing is actually the rare event here. So the most crucial point is this: the default behavior, the normal thing for a number moving through bubble sort, is to land among strangers. That whole idea that numbers were somehow magnetically attracted to their neighbors, totally busted. But, and this is where it gets really fascinating, in that rare 22% of cases when pairing does happen, it's not random at all. A number almost exclusively pairs with the number that comes after it. So like a 5 landing next to a 6, pairing with the number that comes before it, like a 5 next to a 4, it's practically zero. It almost never happens. This is the algorithm's hidden fingerprint. So what is really going on here? Why does the algorithm behave this way? Well, the answer reveals a much bigger idea about the relationship between what we think of as randomness and what's actually just rules. You see, on the surface, the journey of one single number through the sort, it looks chaotic. It looks totally unpredictable. But it's not. Bubble sort is what's called a deterministic algorithm. That means if you give it the same starting list, it will make the exact same swaps in the exact same order every single time. No exceptions. The randomness we think we see is just what happens when its simple, rigid rules interact with a shuffled list. So the big takeaways here are pretty cool. First, real stable patterns often only show up when you look at things at a very large scale. Second, an algorithm's internal mechanics, like bubble sort's simple rule about swapping neighbors, they create their own unbreakable laws of physics in a way.
And finally, something that can look completely random can actually be perfectly predictable if you just know the starting point and the rules of the game. It all leads to this really powerful idea. What we perceive as random isn't always truly random. So often, it's just a system with simple deterministic rules that are playing out in a way that's just too complex for our brains to easily predict. And that leaves us with a final thought to chew on. From the flocking of birds to maybe even fluctuations in the stock market, what other things in our world that we just write off as random are actually just the beautiful, complex results of a few very, very simple rules working in disguise?